Welcome to the third Organic Chemistry podcast, or what I like to call Dr. Brian Lloyd's Scribblecast. In this Scribblecast, we'll be taking a look at bonding and Lewis structures. We'll be continuing with our look at electrons, as we have covered them in atomic structure, and start utilizing them to build, as what you see here, the chemical bond. Bonding is important because it is what allows atoms to come together and build molecules. Through the chemical bond, organic molecules can be built. So we need an understanding of bonding before we actually can construct the molecules themselves. The first term we need to define is the chemical bond. As it's written here, the chemical bond can be defined as a force of attraction between two or more atoms. In actual fact, one might ask the question as to why atoms bond at all. Bonding will occur if atoms can reach a lower energy state. If atoms can achieve a lower energy state through some kind of electron-electron interaction, they will do so. Because of this, bond formation always corresponds with the release of energy. This energy must be put back into the molecule if you want to break a bond. In other words, if energy is released when a bond forms, that same amount of energy must be put back to break that bond. Because of this, this energy is referred to as the bond dissociation energy, sometimes given the letters B, D, E. As the bonds get stronger, more energy must be put in to break those bonds. Now, this bonding, or the chemical bond, comes in three versions. The first one we're going to look at is the ionic bond. Now, I'm not going to write out the whole definition. I'm going to read most of it, but I will write down the most important part of it that allows you to distinguish it from other types of bonds. The ionic bond may be defined as the electrostatic force of attraction between two ions formed by, and this is important, so let me say that again, it's the electrostatic force of attraction between two ions formed by the transfer of electrons. In other words, this is a bond that results when electrons from one atom are completely transferred to another atom. This results in the formation of ions, positively charged or negatively charged atoms. Hence, the ionic bond is referred to as electrostatic force of attraction because it's a force of attraction between point charges. Let's consider an example. Chlorine. Chlorine is atomic number 17. It's found in the third row of the periodic table. Chlorine 17 has 7 valence electrons. In the n equals 3 shell, there are 2 in the s and 5 in the 3p. So chlorine has 7 valence electrons. Here is its Lewis dot diagram. Now, it turns out that atoms typically are trying to get to a lower energy state for bonding, and we've already mentioned in our previous lecture that filled shells represent or correspond to low energy states. And it turns out if you can get a completely filled shell, okay, by filling the S and the P subshells, you get to a lower energy state. Now suppose we react this with a calcium. Calcium is in the fourth row. Calcium is atomic number 20. And as you see, it has 2 electrons in its 4s, its outermost, so it has 2 valence electrons. Now we can react this with another chlorine. I'll put its 7 valence electrons around. Now, in this case, what can happen is calcium can release one of its electrons to a chlorine, and that'll give chlorine a full 8 electrons, completely filled SMP, a completely filled shell. By doing this twice, calcium loses 2 electrons, which means it empties its 4s, empties its 4th shell, and it's only left with a completely filled 3rd shell. In other words, both calcium and the 2 chlorines get to filled shells. And this is energetically stable, favorable. And so what happens is we get chlorine, and I'm going to represent my 2 dots, or 2 dots in lone pairs, with a dash, with 2, 4, 6, 8. And that's a negatively charged chlorine because it's picked up an extra electron. We have a calcium who's lost, emptied its outer shell, so I'm going to leave that as, and it's lost 2 electrons, so it's now 2 plus. And the other chlorine, okay, and I'm going to put dots for that one, just so you can see that you can represent these lone pairs as 2 dots or a straight line. And it's negatively charged. What we've produced here is the salt calcium chloride. Right? So in such a bond, electrons are transferred until each ion has acquired 8 valence electrons. This is often called the noble gas configuration. Now, what are some special features of these ionic bonds? Well, such ion bonds typically form between atoms of opposite ends of the periodic table, or what are referred to as metals, like calcium, and nonmetals, like chlorine. We get ionic bonding if the electronegativity difference is greater than 1.7 in the Pauli electronegativity values. Notice that these ions will attract a chloride in all directions. I mean, the positive charge will attract negative charges and in any direction. In this sense, the force of attraction from the 2 plus is said to be omnidirectional. And the last thing is ionic bonding is typical of ionic salts, like table salt. Sodium chloride utilizes this type of bonding. Okay. One last point about ionic bonding, you can get it in molecules that have other types of bonding in them. And so you get a combination of ionic and what we're going to cover next, called covalent bonding. Let me just draw an example of a molecule that has that. I'll write that right below the ionic bond. This will be an organic molecule that is actually a salt, and it has some covalent bonding in it. And we'll define covalent bonding shortly for you. So here is a molecule. I'm going to write it CH3, CO2. This unit of the molecule has no ionic bonding, but this unit can be negatively charged to an ion. So while there's other types of bonding in here, this whole unit is negatively charged. And it can have whole molecules that act as a charge. NH4 is a positively charged derivative. And this material is referred to as ammonium acetate. And it has an attraction between the NH4 plus and the CH3CO2 minus. So you can have very complicated molecules that are salts and have ionic bonding in them. Okay, let's look at the next type of bonding, which is referred to as the covalent bond. Okay, sharing of electrons. Now these bonds will form just like ionic bonds until a noble gas configuration is achieved. But since the electrons are shared, they can be counted as being available to each atom of the bond. Now, the measure of the ability to share electrons is known as valency. If an atom can form 4 bonds to get to this noble gas configuration, it is said to be tetravalent. An example of a tetravalent atom is carbon. If you only can form 1 bond to get to this type of sharing, noble gas configuration, you're said to be monovalent. Hydrogen and the halogens, that is fluorine, chlorine, bromine, and iodine, are monovalent. Example of divalent atoms, atoms that will form 2 bonds to get to noble gas configuration, are oxygen, sulfur. And trivalent atoms are nitrogen and phosphorus. Let's look at an example of a covalent bond, such as we get when we have carbon. As I said, carbon is tetravalent. Why? Well, if we look at the electronic configuration of carbon, carbon will be 1s squared, 2s squared, 2p2. And you can check that out and draw it for yourself, but what's important is the valence electrons. And I said 2s squared, 2p2, that means carbon has 4 electrons, 4 valence electrons. You can determine this by looking at the periodic table, finding what row carbon is in, and counting from the left. If you do that, you see lithium, beryllium, boron, then carbon. If I count from the left, that's 4. That means it has 4 valence electrons. So the periodic table even gives you this information. So let us continue, and let's put in our 4 valence electrons. And now let's bring in a monovalent atom, such as hydrogen. Hydrogen has only 1 electron. And I'm making it a bit small. Hope it's not too small to see. But I'm putting 1 electron. Now, hydrogen, to fill its shell, there's only in the first shell, there's only the 1s can hold 2 electrons. So hydrogen wants 2 electrons. Carbon, on the other hand, to get a completely filled shell, wants 8. How can it do it? Well, we can share the electrons. If we share these electrons, each hydrogen ends up with 2, and it fills its shell. Carbon, on the other hand, by sharing can count all the electrons as well and gets 2, 4, 6, 8 electrons. This molecule is CH4. Methane gas. Methane gas is an organic molecule that has covalent bonding in it. The bonds are formed by the sharing of electrons. You'll notice that covalent bonds are slightly different. The force of attraction here is between the carbon and hydrogen, so it's a very directional bond, whereas the positive charge in ammonium can attract things from all directions, okay? So you could have something being attracted to the plus here, attracted to the plus from here, attracted to the plus from here. The ammonium plus attracts things from all directions, all right? So you could have your negative charge coming in from any side. Well, it turns out that because of the nature of the sharing of electrons in covalent bond, the covalent bond, the hydrogen, the bond that forms here is very directional, okay? And sometimes, though, you will end up with molecules that have electron pairs in which there is no bonding. I said nitrogen, for example. Nitrogen was trivalent. Why did I say nitrogen was trivalent? Well, nitrogen is trivalent because nitrogen has atomic number 7, 7 electrons, 1s squared, 2s squared, 2p3, but in the outer 2 shell there are 5 electrons, So nitrogen has 5 valence electrons. It's trivalent because to get to 8, the noble gas configuration, nitrogen only needs 3 bonds. And what we get here is the molecule NH3. Now NH3 ends up with these 2 electrons that have no bonding. They're not bonded to anything. And so often they're referred to as a non-bonding pair of electrons or a lone pair of electrons. So in covalent bonding situations, you may actually have electrons in bonds, and there may be electrons on the atom that are not bonding. Now, the reason I bring up these electrons, non-bonding electrons, is sometimes they can be used in bonding. How? Well, this brings up our third type of bond, which is called the dative bond. It's often called the Dative Covalent Bond, or the coordinate. Now, this dative coordinate bond is a covalent bond. The only difference is in where the electrons came from when the bond was formed. What do you mean? Well, let's erase this, and let's look at NH3 for a second if we can. And NH3 is an example of a base. Bases, we know, like to react with acid. An acid is simply a proton, a hydrogen that has lost its electron. So if we have this acid, H+, and it reacts with the base of ammonia, that means the H will form a bond to nitrogen. The interesting thing is hydrogen, H+, has no electron. These neutral hydrogens, hydrogen from the periodic table has an electron, but if hydrogen loses an electron, it becomes H+, becomes a free proton. If that proton reacts with ammonia, it will form a bond. The 2 electrons from the end will go and make a bond. This right here is a new bond. This bond is referred to as a dative or coordinate bond because the 2 electrons come from the nitrogen to the H. This is how we form the NH4 plus unit over here. Now, you might say, well, is this hydrogen bond different from the other 3 hydrogen-nitrogen bonds? And the answer is no. If you looked at NH4 plus, you could not distinguish between any of the covalent bonds in the NH4 unit and assign one as dative in that. Well, if they're all the same, why do we even go with this definition? It has to do with how the bond is formed. In this case, CH4, you had hydrogen with an electron coming in and carbon with 1 electron and those 2 sharing. In the case of nitrogen, once we had ammonia and we had a lone pair, both electrons came from the nitrogen. So it's really all about where the electrons came from in the bond formation, and it has nothing to do with the final outcome. In other words, that once you're done, once you form the bond, there is no difference between a covalent bond and a dative covalent bond. All right. These types of bonds and understanding this type of bonding is very important in allowing us to be able to build molecules. And one way of building molecules is through valence bond theory. Now, we're going to actually look at bonding theories in a little while. But what we want to do now is take our chemical bonding definitions and come up with a technique for constructing molecules that are called Lewis structures. Now, we must remember that if we are going to draw a Lewis structure, we must show all of the valence electrons, all of the bonding pairs, and all of the non-bonding pairs in a molecule. The molecular formula may be defined as the true formula, or the formula that shows the real number of atoms in the molecule. Now, we need some rules when we're given a molecular formula. And I'll write down a couple formulas so that when we can come to this molecule that we're going to attempt to draw a Lewis structure for, we don't get confused. Let's consider some examples. H2O. If you were asked to draw a molecule of H2O and show just the bonds, I'm not going to show the lone pairs to begin with, most of you would recognize that H2O may be symbolized by this. If I wrote the molecule CH4, which we just previously had on the screen, you all would have no problem recognizing that it means this. And I'm not worrying how the H's are drawn, whether they're drawn in a square or not. The point is, you recognize that H2O meant 2 H's bound to oxygen. CH4 meant 4 H's bound to carbon. You wouldn't write or ch. So a general rule will be, if I give you a molecular formula and I say Cl2CO, that means 2 chlorines bound to carbon. If I wanted something like this, I would have to give you a linkage pattern. What do I mean by linkage pattern? I would actually have to write in square brackets something like, and the line I'm drawing between the Cl's and the C's would not be a bond. It's just showing how they link up. So if I wanted something different than 2 chlorines bound to carbon, I would have to draw it for you. So here's our example. It's Cl2CO, a toxic molecule known as phosgene. And what I want to do is draw a Lewis structure, a structure that shows all of the bonds and lone pairs in this molecule. Well, what's the first thing you must do when determining a Lewis structure? The first thing you must do is determine the total number of valence electrons. How many valence electrons does chlorine have? Now, if you're having difficulty at determining the number of valence electrons, you can determine it by counting the number of spaces in the row of the periodic table in which the element's found. What do I mean? Well, look at a periodic table and find chlorine. If I count across the chlorine, and typically we skip the transition metals, but for all the examples we work in, we don't count the transition metals. I could count chlorines in the third row. I could count from sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. If I count 1, 2, 3, 4, 5, 6, 7, chlorine has 7 valence electrons. There are 2 chlorines, so I have 2 times 7. The next thing is carbon, if I do the same thing, has 4. And then oxygen has 6. Okay. Now, I must watch for charges here. If there was a charge, like a 2 minus, I would have to add 2 extra electrons. If there was a positive, I would have to take away 1 electron. If there was 2 plus, I would take away 2 electrons. So I must watch for charge and put that in. If I add these up, I get 2 times 7 is 14, plus 4 is 18, plus 6, 24 electrons. So carbon has 4. Oxygen, I said, has 6, so I'll put that in. 2, 4, 6. Chlorine has 7. Now, if this molecule had a negative charge, I would put in an extra electron someplace. All right. If I had a positive charge, I would erase one of these electrons. And really, it doesn't matter which one you erase. Typically, you would choose the more electronegative atom to add electrons to, and the least electronegative atom to take electrons away. But that's not absolutely crucial. And you can make your solution to Lewis structure work no matter where you take an electron from or add the electron. Now, I start joining up electrons to make filled octets or noble gas configuration. For example, chlorine has 7 valence electrons. To fill its shell, it needs 1 more. So he can share 2 electrons. If he shares these 2, now these 2 that are shared can be counted both for chlorine and carbon because she's sharing them. So 2, 4, 6, 8. The chlorine's happy. He's got a filled octet. Now we see carbon gets to count the chlorine, but that's 2, 3, 4, 5. So carbon still needs to make more bonds. Now we keep making these bonds until we get 8 electrons around every atom. So the other chlorine shares. Now we've got 2, 4, 6, 8 around the chlorine. 2, 4, 6. Carbon's not happy. Carbon still needs to get 2 more electrons. Well, he could start bonding with the oxygen. If he makes a covalent bond with oxygen, the carbon is not happy. It still has 2, 4, 6, 7. It wants 8 electrons. No more atoms to bond to. If you run out of atoms, then continue bonding to an atom by making multiple bonds. And you can have single, double, or triple bonds forming in carbon-based molecules. We'll talk more about that later on. So carbon is not happy. Oxygen only has 7. It's not happy. So if oxygen and carbon make a second bond, now oxygen can count those 2, its lone pairs, 2, 4, 6, 8. And carbon gets to count 2, 4, 6, 8. All of the atoms have a filled octet around them. So now we can draw the bonds as straight lines. And we must show the lone pairs. In this case, you can show the lone pairs as straight lines. Or you can put in dots. Please pick one or the other. Okay? And this guy is lone pairs. So there you have it. I've drawn the Lewis structure for the molecule phosgene. Why did I draw the chlorines bent? I don't have to. I could have drawn them straight out. That's fine. One last double check you can carry out is to make sure that the lone pairs, the bonding, non-bonding pairs, and the bonding pairs all add up to 24. Each line represents 2 electrons. So count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4. So I got 24 electrons. That checks with what I should have had, and so I know I haven't made any mistake. All right. Now let's try this again with a different molecule, this time one that has a charge, and do the same thing. So I'm going to give you the molecule NO2 plus. Okay, so what do I get if I add up this as a total number of valence electrons? Well, how many electrons does nitrogen have in it? Well, if you count across in the row you find nitrogen, you get lithium, beryllium, boron, carbon, nitrogen. You count across the periodic table, you see 1, 2, 3, 4, 5. Or I could do the electronic configuration. And nitrogen 7 is 7 electrons, 1s squared, 2s squared, 2p3. But I'm only interested in the second shell as the valence electrons. Nitrogen has 7. No, the 1s are buried. Nitrogen has 5 valence electrons. We have oxygen, oxygen, 2 oxygens, each oxygen, so 2 times 6 valence electrons. And now we must subtract 1, minus 1, minus 1, minus 1 because of the positive charge. All right. Now if I calculate this, I get 5 plus 2 times 6 is 12, 5 plus 12 is 17, I get 16 valence electrons. So when I'm done my structure, I will want to check and make sure that there are only 16 valence electrons in the structure. Okay, so I can begin drawing my structure. And so I can put down my 5 valence electrons around nitrogen, my 6 valence electrons around oxygen, my 6 valence electrons around oxygen, and I got to remember to take 1 electron away, so take 1 electron away, I just take it off nitrogen, and I'm ready to proceed. And at this point, you should be jumping up and down in your chair, screaming, "No, Dr. Lloyd." Boy, is that lame. Okay. In actual fact, what have I done wrong? What I've done wrong is forget that NO2 means 2 oxygens bound to the nitrogen. And we can take 1 away. Now you may say to me, why are you taking 1 away from nitrogen? I took it away from nitrogen last time. But in actual fact, you can put the electron anywhere. So let's take it away. I'm going to actually take it away from an oxygen just to show you can actually get this to work. Now, it'll be a little difficult, and we will actually have to incorporate the concept of dative bonding. So if I take it away from oxygen, actually let's do it twice. So I took it away from the nitrogen on the bottom, NO2, and from the top I took it away from the right hand oxygen. So let's start with this. We have to put 8 electrons around every atom. Okay, so let us begin. If I do this, I can start with this oxygen and I can covalently share 2 electrons. If I do that, 2, 4, get to count both because it's shared, 6, 7. Oxygen's not happy. We still got a lot of room on nitrogen, so I can join this guy. The oxygen now has 2, 4, 6, 8. So oxygen's happy. How many we got in nitrogen? 2, 4, 6, 7. Oh, well, I can join these 2. Ha! Nitrogen now is 2, 4, 6, 8. Nitrogen's happy. Oxygen's happy. Both have filled octets. What about this oxygen? 2, 4, 6. Only 6 electrons. What can we do? We can't share. This nitrogen can take its 2 electrons and donate them in a dative bond so that oxygen can count them as well. If it does this, the nitrogen's still sharing, so it gets to count them as well. 2, 4, 6, 8 for the nitrogen, 2, 4, 6, 8 for the oxygen. What do you end up with? You end up with that. Well, could I get that from if I pulled the electron off of nitrogen? And I'll do that quickly. Sharing these 2 electrons. 2, 4, 6, 8, 2, 4, 6. Well, share that, those 2. And this one can come around and grab that. This oxygen, 2, 4, 6, 8. Nitrogen is 2, 4, 6, 8. Notice by pulling the electron off nitrogen, I got the same thing. So in the top example, I pulled the electron off the right-hand oxygen. In the bottom example, I pulled the electron off of the nitrogen. The bottom example, the simple thing was I didn't have to introduce the dative bond to produce my bond, but notice the whole goal is to get 8 electrons around every atom. Now, last thing to always do is double check. I need 16 valence electrons. Count up your electrons. 2, 4, 6, 8, 10, 12, 14, 16. Okay. Now, this example, the NO2 plus, does raise a question. Because there's a positive charge in NO2, one could ask, now that we've got the molecule structure, where is the positive charge? In actual fact, does the positive charge exist over the whole molecule? Or is it on an oxygen? Is it spread out over 2 oxygens? Is it on the nitrogen? We can do a calculation which will allow us to determine the actual formal charge for each atom. Now, typically we do this for non-hydrogens. If there's hydrogens, we don't do the calc on them because typically hydrogen has no charge. But what we want to do is do a calculation counting electrons to find out which atom has that positive charge on it. And this is called formal charge. We want to calculate the formal charge of every non-hydrogen atom. That I can do. But what is formal charge? Well, formal charge is the charge an atom would have if the electron it shares with other atoms was shared equally. In other words, it assumes equal sharing of electrons in the bonds. Now, electronegativity, we know rules this out, but for the calculation purposes, we're going to assume that electrons are shared equally. If we make this assumption, we can calculate the charge that an atom would have. How? Well, formal charge will equal the valence electrons of the atom, of the neutral atom. So it's just its valence number. And you get that from the periodic table. Electrons assigned to the atom on the basis of equal sharing. So if there's a bond between 2 atoms, and the electrons are shared equally, we will count, for the purposes of formal sharing, 1 electron in the bond for one atom and 1 electron for the other. Let's do a calculation for these two, and since this oxygen is identical to this in the sense that it has a lone pair, a double bond, we could treat them the same, but I will label them differently. So we got 2 oxygens. Let's call one oxygen alpha and one oxygen beta. Okay, let's start with oxygen alpha. So we want to calculate the formal charge of oxygen alpha. And that will equal its valence electrons, which is 6. Oxygen has 6 valence electrons, minus, let's come over and look at oxygen alpha and count electrons. Well, this is a lone pair. There's 2 electrons in a lone pair, and they're not bonding. They're stuck in oxygen, so they both count for oxygen. This lone pair, 2 electrons, we count them for oxygen. Here's one bond of the double bond. It has 2 electrons in it. We're going to count 1 for the nitrogen, 1 for the oxygen, so you get 1 for that bond. And this line's another bond of the double bond. And again, 2 electrons in it, so we're going to count 1 for the oxygen, 1 for the nitrogen. So what do we get? Lone pairs 2, lone pairs 2, 1, 1, 2, 4, 5, 6. 6 electrons, assuming equal sharing. And what do we get? Equals 0. How about formal charge oxygen beta? Formal charge of oxygen beta equals 6 minus, well, if we do the same thing, 2, 4 for the lone pair, 5, 6. 6 minus 6 equals 0. And lastly, we have formal charge of our nitrogen. What is the valence electrons of nitrogen? Nitrogen has 5 electrons, and we have bonds, no lone pairs, so we count 1 for each bond. 1, 2, 3, 4. 5 minus 4 equals plus 1. Now when you're done, you always add up to get the net charge. You always add it up to get the net charge. And if I add this up, 0 plus 0 plus 1 is plus 1. This number should match the charge originally given to you. If it doesn't, you've done something wrong. And since it does match, we know we've done everything correctly. So what does this tell us? This tells us that the positive charge is on nitrogen in this Lewis structure. So we've not only calculated or produced the Lewis structure, we've actually calculated the formal charge and determined that the positive charge resides on nitrogen. Now, why don't you do that for the phosgene molecule we finished? Don't be surprised if you find out all the atoms have 0 charge in that case. They do. You should be able to double check that. You might suspect that because phosgene, Cl2CO, has no charge. Be careful though. You can have molecules that have no charge, which when you do this calculation, you end up with a -1 and a +1, and when you add it up, they cancel each other. And the charge overall is 0. And that can happen. So don't always just assume there's 0 charge on every atom.